what I really want to talk about is lecture A, recurring meaning. What is the recurring meaning? Let's first see about. I will introduce you some modes. Like we will introduce recurring meaning. We will also introduce modes of free existence. We will introduce geometric interpretation, and we will also later describe about state response, the impulse function. So let's see about recurring meaning first. Recurring meaning ST and S0. We can start from the IO relation or from state space. S dot will equal AS plus BU as ISO system. YTUT belongs to R. Y equals CS plus DU. This is the relation. This is the relation we have talked about before, right? And our system is ST, so let us invert the system by differentiating YT so many times until we get an n times n system of linear equations. So the first one is we know the output, then we should do the derivative of it. So do the derivative first time, you will get this one, right? And later you using the operator, because for S the operator of it will A, so CA, and for U the operator for it will not only be B but also be D, right? So we do the operator D DU dot DB CB CBU DU. Okay, the coefficient of it, that operator will be CB. Okay, and later keeps the dot, it will be DU dot. Okay, next time we do the Y double dot. Y double dot is using the Y dot. So CAS dot. CAS dot I have talked about before. The coefficient of S variable would be A. So CA square S. And for U, the coefficient for it now would be A. So we take CBA. Next, for U dot, we should keep the CBU dot and plus DU dot, keep them together. For Y dot dot. Okay, as before, as the last way we can get this formula. Do not worry, you do not very clear about it because it's just a rule and I am not always very clear about it. So I can only talk about the generation situation now for you. We need an equation. This means differentiating up to y to the n minus 1 power, in which S appears linearly. It's a linear n times n symmetric system in S. Let's write it in compact form. So the compact form is like this way. Like this way. One is the output, one is the input. Okay, we use capital Y and capital U to represent them. For the capital Y, the system, the output will become, the coefficient will become CA squared to the C to the n minus 1 power, okay, times ST. And for the output, it will become CB, okay, C to the n minus 2 power B. And the diagonals is D. Okay, for instance, the first row above contains y equals cs plus du. So C is now vector, is a new vector, indicates as C. This is simple. The second row contains this one, and so on. The third row, just the row you have seen in this way. We do use a metric to represent it now. Later, let's know. We get metric M0 and T. Maybe you will confuse about what are they. Actually, we just represent this one to M0, this one to T. We use capital M0, capital T to represent these two metrics. The way we do that is helping us more simply, okay, do the thing. We get the metric M0T, and now we need to find the value of S by instating of it. So how could we get this one? Just use the mathematical, but the mathematical in metric knowledge. Okay, now you can get this one. Okay, you can first you do this minus this, and then you times the M inverse, M0 inverse. So we need M0 invertible. The determinant of it should not be 0. So we call M0 is the observability metric, also indicated as O, capital O. We can also indicate it. The state variable ST are expressed as a linear combination of YT and its derivatives and VT and its derivations, while M0 and T are constant matrices. The system is called observable if M0 is non-singular. Observable. So why we call it observability metric also. Okay, if M0 is non-singular, because we can observe the states. Note, the observed form always produces AC matrix, so that the resulting M0 is non-singular. The system is observable. Let's see next. After that, we want to give you an example. We take the last example, y dot dot plus 3 times y dot plus 2 dot y equals 3u plus 3u dot plus 2u. As you can observe, this is the form that with the input have the derivative and also the output have the derivative, right? So we can recover the meaning of ST by using MO T, where M equal to M represents the derivative, second derivative, okay, second derivative, the biggest derivative, okay, the biggest derivative appears. We just use the M because we have no M is represent this matrix. I have shown you this matrix, okay? This one. So you just take them like, let me think about it. C, 2, 3, minus 6, minus 7. Yes, maybe this is the metric he given you, okay? He given you. And this is also the metric he given you, okay? And later, we just do some determinant to make it not zero, to make sure it is the non-singular one. We're using the derivative equation. We have a derivative for last. So S1, S2 could become this one. You just take the transpose T to here, right? You just take the M0 inverse here. So M0 inverse has the formula of it. Okay, it should divide it by the determinant of it. But I see it have divided the minus determinant of it. Yes. I will try to explain it later in the next lecture because I am not sure about these classes now also very much. Okay, I will ask my friends, ask my teacher, ask internet to search it so that we can give a physical meaning to the states. Moving to the initial condition as O, let's define our input formula. Why we need to define this? Because sometimes the function will not always be zero. Okay, will not always be zero. Let's see next. This singular reduction, okay, explains that a discontinuity in t equals 0. If we approach t equals 0 from the positive values of t, then we get non-zero values, for instance, in the input. But if we approach t equals 0 from the negative values of t, then we get 0. The convention is about taking as 0 at t equal from the negative 1, okay, limit. That is the limit to minus epsilon, approaching from the negative side. This means that the input has not influenced the system yet, since it's approached from the negative and equals 0, right? Then we can use this one, okay? The transfer, the u, the later plus will equal 0. And we use the m inverse we have, use the y0 we have. This should be the problem they're giving us, because here we just shows an example, so we do not talk it very clearly. And later we calculate the value of it. So now we can continue the example and get as t will equal e to the at times s0. Actually, you may be very curious about this formula, but this formula is just a derivation from other methods. It helps us to find out this kind of metric solution. This is just a method, and I could not explain you because I also do not know. But we can know how its application. Note, the goal of this example was showing that in some cases, the way to connect y0, y dot 0, and so is through the observed form. Okay, it's through the observed form. Okay, after that, we would like to introduce the modes of resistance. How can we introduce the modes of resistance? We will see such example in our tutorials later. System S star equal AS, you know this. And we will always know the initial condition. From this, we can get the solution of ST, right? Let's try to better understand the meaning of the solution from the geometry standpoint. We assume A as diagonalizable. Here is a transformation that makes it diagonal. Recalling what we know, eigenvalues lambda I equal lambda 1 to lambda m, eigenvector we know. And you should know the definition of the eigenvector from algebra, okay? And similar transformation metric, you will find that how the M metric come from is from the eigenvalue 1, eigenvalue 2. It would always stand by this way, eigenvalues in the columns. And diagonal metric, it would become this one. It will become this one, okay? And the lambda 1 to lambda n will add the diagonal. And for the inverse of similar transformation, the transformation metric, we will use this one to represent it. Okay, this is just a simple introduction. It's like show you how we represent M inverse the metric M. So the last equation makes sense for this reason. Let's take this one to this characteristic and multiply by M to the minus 1. Because if we multiply by M to the minus 1, it would become M to the minus 1 times A equal lambda M to the minus 1. And if we have already, what's the lambda? Is the eigenvalue. Is the eigenvalue. So we have to know how to use the metric to represent the form, okay, the formula when of algebra, okay, of algebra. Okay, later we should know another property of M. Another property of M. It's like it can equal 0 and equal 1. And for n times n inverse, it will equal identity. Okay, it will equal identity. Let's introduce it more about modes of free systems. Free systems response ST equal e to the AT times S0 metric. Okay, this is the free systems response. This is the free systems answer, something like this. And we also know the relationship, something like this. Okay, and now we're using, we take, let me see. We take this one into this, okay? And we paste this one into this. And we paste the inverse into this. Okay, this is the S0. It's A. It's this one, this metric. Let's define UI from the last two metrics and right. It will become this one. Function will become this one, including also e to the lambda t. Into this definition, we can get the final answer. Okay, we conclude this one into this sum of equation. So the solution state vector is a linear combination of the motion along a direction given by the eigenvector multiplied by a function, while the time rate depends on the eigenvalue and of the excitation of the modes related to the initial conditions. The initial condition can excite to a given mode shortly, or weakly. This giving us a geometric representation. Let's see the example. We have defined the meaning of this one. And this is the S0 we call alpha times VI. ST is the solution we have talked about before. So if the initial condition is a scalar alpha multiplied by the angle vector VI, then the solution is just moving along this direction. In other words, we only excite mode 1 so that all other modes don't appear. In general term, if S0 equal alpha k times UK, UI will equal alpha k 0. ST will equal alpha k times e to the lambda kt times square k. If sk S0 will become the sum of that, then the function's solution will become the sum of them too. Thus, a mode appears in the solution if and only if it is excited by the initial condition. Let's see the geometric interpretation. The geometric interpretation of ST for n for the derivative of it will be 2. So S will be the transpose of it, and we can plot difference. We can plot different trajectories of the systems respond to different initial condition on the state space since n equal 2 is of them. We can do that based on the decompositions of the metric A. Examples. Let's see the example. I have given you the metric of it, okay, and giving you the form of it. So let's plot the solution for differential initial condition. We start from the point S0 at time t equals 0, and then we find other points by varying the value of t. This is the procedure. We first calculate out the eigenvalue eigenvector, and later we can show the eigenvalue and eigenvectors, show the solution at this way, because we have know how could we write the solution from upward, right? First u1 as 0 and times the eigenvalue eigenvector. The form of it is here, okay, is here. For u1 for eigenvalue for e to the power of t, e to the lambda power of t, e to the power of lambda t, okay, of lambda t. u1 as 0 and u2 as 0, okay? We just take into the formula we have derivative above to get the solution of this one. And next, I would like to show you the example, and I want to tell you how could you draw it. How could you draw it? So, example, negative eigenvalues. Here we give you the problems like this way. And from this, you can calculate the eigenvalue, you can calculate the eigenvectors. Okay, let's take the solution in this way. This for the eigenvalue e to the lambda mt. Lambda is the eigenvector. Oh, sorry, this is the eigenvector, and lambda is the eigenvalue, and this is the u1, u2, okay? And chance of the solution. If we start on the lines, only one mode is excited, then the solution is converges. What's that mean? Because the e power minus n will be converges, and e to the minus 2 power will also be the converges. So we converges to 0, converges to 0. It's this way. And let me think about the chance of the solution. If we start on these lines, only one mode is excited, then the solution converges. Then the solution converges. Okay, like line 1 and line 2. And line 1, as you can see, is drawn by, because the vector eigenvector is 1 minus 1. So we find the coordinate 1 minus 1, and then we draw this line. Okay, then we draw this line. And for vector 2 is 1 minus 2. So we draw this line using the same method again. After that, we see this convergence or non-convergence. Okay, it converges. It converges. It will start outside of those lines. The solution converges remaining inside the section defined by the lines. For t to the infinite, okay, this one was smaller than this one, so we have converges along v1. For t to the 0, we cannot say anything about the exponent. But s dot, the tangent of the line, tells us the direction chosen to leave as 0 dot. So dominates and the solution start tangent to v1 and then rotates to go to 0. This is the example I want to talk about. So next, we talk about another. If I give you a solution like this way, how could you draw? First, we're using the eigenvector 1, 1 to draw this line, and minus 1, 3 to draw this line, right? After that, we do the convergence or divergence decision. For this one, it would be the divergence, right? So we convergence for this one, but divergence with this one. Oh, actually, let me think about it. The real drawing is not something like this. The more professional drawing should be in this way. Like near here is divergent, right? So you draw the arrow like this. Near the line here is convergent, right? So you draw the arrow like this. From this arrow to this arrow, you can draw like this. This arrow to this arrow, this arrow to this arrow, this arrow to this arrow. So this is why I can draw this curve. This curve another drawing I can draw from my eyes. And so about this teaching is also not right. For the vector y minus 1, it would this line, right? For y minus 2, it would this one. For all of them are convergent. So points to this, points to this, points to this, points to this. So this is why I draw here. And I draw here. Or maybe draw here. And draw here with the arrow pointing this way. So you will find it easy, maybe. But I want to show you the complex one. Yes, the complex one. So don't be afraid about the complex one. For this example, complex eigenvalues, right? The lambda, you have no. The solution you have no. So let us draw. But you will find that this is the complex eigenvalues, eigenvectors. So actually, if it is have a rule, if the real number of it would be 0, then the shape of it would be a circle. Okay, would be a circle. And if the and later, let's see, if the alpha is bigger than 1, because for alpha bigger than 1, it would become e to the alpha t. It would become divergent. For the alpha smaller than 1, it would become convergent. So for convergent, it will convergent to 0. So it rotates like this direction. But for divergent, it will convergent to infinite. So it rotates like this direction. This is the difference for alpha. Z equals 0, bigger than 0, and smaller than 0. So let's see the example complex eigenvalues with a real input. Okay. If we start with this one, we can stay there. Now the solution can be written using this one and this one. That is a combination of an exponential with an oscillation. So we have a spirit that divergence and all that convergence. As before, we have a real solution. We stay on the plane as long as we have a real S0. For the direction of the spinels CW and CCW, we need to know A and S0. The plots before are just an arbitrary illustration. So what happened for large values of U? We can plot the results, but the formula is still valid for this value. After seeing so much example, you can tell me what the meaning of each parameter. This one is represent the eigenvectors, eigenvalue, and this one may be the initial or the coefficient, I think. So S0, if the initial condition is equal to this one, then only mode K is excited. ST is equal alpha times the E lambda KT times VK. So the solution travels along VK. If S0 is equal alpha 1 times B1 plus alpha 2 times B2, then the solution involves a linear combination of the first and second eigenvector. The solution stays on the plane and is obtained with superposition. ST will equal these things. If you only have 2, right? So now note, if the matrix A is non-diagonalizable, then the equation ST given above doesn't hold. Let's see the stats response. Consider a LTI SIOS system given by this formula. This is the formula we have seen before. So ut is equal 1t will equal 1 when t is bigger than 0, and will equal 0 when t is smaller than 0. Steps function. We assume S0 equals 0. If they are not equal 0, we can superpose the effect of the non-zero initial condition and the effect of the steps input. So let's find st and yt. St will equal e to the at times s0 is the solution we have talked about before, right? And for the later, maybe it used for particular solution, I do not know. But now we have given you the responding solution. So you should take them together. Talk is only for positive time. It goes from 0 to t. So u talk is equal 1. Let's focus on the integral by recording the scalar k. Integral, how to integrate it? Using the integral technique. You can integral and get the solution right this way. Now let's replace the scalar a with the metric a. We take the place by this metric. Okay, we first using the solution. We first using the calculation of scalar. Then we take it into mass inverse. Determine a should not be 0. That satisfies the initial condition. Put t equals 0, and the equation s r equal as plus bu. For the output, yt will equal cs plus du. And from the before, we have got this x solution. So we take this x solution into here. Okay, and now the output is the condition we have given when t is bigger than 0. If a is singular, then we can't use this quick formula, but we need to hit each other separately. We don't consider this seminar. Let's see another knowledge. It is about impulse function. First, we start with the pulse function ut equal delta over and 0 else. For this equation, you can draw the picture something like this way. It can be written as ut equal 1t minus this one, where the second step function is slightly by time delta. The scaling with 1 over delta is an unit area. The impulse function is the limit case of the pulse function. When 1 goes to 0, delta t, and limits delta to 0, u dot t. The height goes to infinitely, but the area is still 1. It's called generalized function because it isn't a real function. In practical terms, it isn't renewable. For instance, dumping a bucket of liquid into a tank infinitely flow rate for an infinitely time that give a finite increases. Okay. So another example is relating a ball with a bat, like F equal ma, a is u, where an infinite force gives a jump in the monumental. The impulse is also known as binary beta function. Let's see the example of the impulse function. Now we're giving an LTISO system. SR equal AS plus BU, Y equals CS plus BU. UT is the delta T, and ST is S0, 0. Find ST and YT. The ST solution is SUU. But now we should use the S0 equals 0. So this one is 0. How about UT? UT will equal delta T. How about, yes, will equal delta T. How about this one? This one he said will equal FT, F tau. Okay. So finally, the function we get is this one. And that is equivalent to the solution of a free system. 0 input and initial equal to B. The output YT is called impulse response, or GT. GT is equal YT is equal to C times ST plus D times delta T. Properties of the impulse function. The first one, it will divide it by divided paragraph function. Okay, divided paragraph function. Area is 1. When your integral is from minus infinite to infinite, it will equal 1. Slightly impulse. The delta t minus t0, 0, and infinite. Okay, and delta t for the reason below, it will become this way. And step function. Let's see the infinite to minus infinite from the positive infinite. Okay, and delta t minus t0 dt, where delta t is bounded. Okay, and from this way is equal 0. And from this one, and from this one, you just take the relationship he has given. Okay, and later we can get the final result in the close vicinity of t0. Ft is equal constant is equal Ft equal t0. So let's see the general input convolution. Let's consider a general input ut and initial condition s0 equals 0. The output is yt equal this one. And because the initial condition of it is equal 0, so we keep this one. It also has the output 1. After that, we're using the calculation we have done before to calculate it, or just differentiate it just now, right now, right? We can get this function. After that, the final result is this one, where the integral of it will equal dut. If we know now the system responds to the impulse we can extract the response to any input with this equation. Yt equal integral 0 to t gt minus tau u tau d tau. The last integral is called convolution because we integrate one function in time and the other in Swifty time. Next one. Let's see the example. The impulse response of a LTI system is gt equal e to the minus t plus e to the minus 2t. Find the response yt when ut is equal e to the t component. Let's apply the convolution integral. So yt will equal this integral. Okay, will equal this integral. And we just using the norm he has given us. Like ut equal this one and gt equal this one. We just take the unknown into this formula. Later we do the integral. So in practical terms, the impulse response is an alternative representation of the system together with I/O relation. And this means because we can extract the system response to any input. Okay, this is finished for lecture 8.